Hello again. We're continuing with 11.5, the alternating series and absolute convergence test, series test. Just to recap what we talked about so far, test of divergence, the integral test, the comparison, the two direct and limit tests. Now we're continuing with alternating and the absolute convergence. And finally, right after 11.5, we're going to finish up those series tests with root and ratio and root tests. So now let's continue with the alternating series test. Alternating series test. So, so far we looked at a series with positive terms. The alternating series test, of course, they will have alternating terms, positive and negative. So in general, we have this kind of series, -1 to n minus 1 times bn, where bn is basically, so all this term, let me write it on the side, this is a sub n, right? -1 to n minus 1 times bn. What does bn really represent? Is the absolute value of an. So when we put this in absolute value, that's what we get. Because -1 to n minus 1 would be positive. Okay, and of course, b sub n is always greater than 0 because it will be the absolute value. Assuming the following conditions are fulfilled. Condition number 1, the n plus first term is smaller than the term before. So, in other words, this is for all n, right? So, in other words, we're talking about a decreasing series, right? So the next term will always be smaller than the previous one. The second condition is that the limit of the absolute value of the general term, which is the limit of bn as n approaches infinity, is 0. If these two conditions are fulfilled, then we will conclude by the alternating series test that the series -1 n minus 1 times bn is indeed convergent. Now, it's easier in this situation to estimate the sum. So to estimate sums, so first of all, we have to make sure that the series is convergent. And if that's the case, then the absolute value of the remainder, as we know, it's s minus sn. We discussed this before. This will be less than or equal to the next term. If this is 10, this will be 11. So this is the estimating of the sum or sums for alternating series. That's what we are talking about. We also have two definitions here to mention, and then we can jump in different situations and problems. So definition. So first of all, if this series, alternating series, is absolutely convergent, it means that is absolutely convergent. It means that this is convergent. So when we say it's absolutely convergent, we mean that the series of the absolute value of terms is convergent. Now, about conditionally convergent. Conditionally convergent. when this is convergent, but this is not, is divergent. So conditionally convergent means that the series, the alternating series, is convergent, but it's not absolutely convergent. So the sequence of the absolute value of terms is divergent. Okay, so we have a few examples to look at here. Let's start with number 3, and I think that that's page 772. It says, test the series for convergence or divergence. So we have negative 2/5 plus 4/6 minus 6/7 plus 8/8 minus 10/9 plus dot dot dot. Let's see how we would be able to write the generic term. Negative 1 to the nth power to n over n plus 4. How do I know this? 2 times 1, 2 times 2, 2 times 3, 2 times 4, 2 times 5, alternating, negative. So the power is n when n is 1 is negative, when n is 2 is positive. And the denominator is 4 plus 1, 4 plus 2, 4 plus 3, 4 plus 4, and so on and so forth, and etc., etc. So this is the sum from n equals 1 to n, from negative 1 to the nth power times 2n over n plus 4. Now we're asked to test whether this series is convergent. Okay, so let's take a look. So we know that a sub n, so that's my page 3. A sub n, we have it, is negative 1 to the nth power 2n n plus 4. And the generic term of positive terms will be 2n over n plus 4. Notice here something interesting, that the limit of Bn as n approaches infinity is not 0. This is 2, which is not 0. So therefore, the series n equals 1 through infinity is divergent by the test for divergence. Okay, moving on to number 9. I think it's on the same page, 772. And this time we have negative 1 to power n e to negative n from 1 to infinity. Again, a sub n is this, b sub n is this, or 1 over e to the n. Same thing. So condition number 1, is bn plus 1 less than or equal to bn? Let's try e to n plus 1 and 1 to e. So obviously this has a bigger denominator than this, so obviously this is fulfilled. So in number 2, we want to look at the limit of e to negative n as n approaches infinity, and it turns out that this is the limit of this, which is 0. Both conditions are fulfilled. Then we conclude that the sum from negative 1 to n e to negative n from n equals 1 to infinity is convergent by the alternating series test. Okay, let's see what is next. Let's look at 13. On page 4. Still on page 772. And we have series n equals 1 to infinity from negative 1 to n minus 1 times e to 2 over n. Okay, very good. So again, to make sure that this is clear, so AN is this, and BN is this. And you notice that the limit as n approaches infinity from e to 2 over n, it's e to 0, which is 1, which is not 0. So then from here we conclude that this series is divergent by the test for divergence. Good. Moving on to, let's say, 20, what is next? 27, yes. This time on page 773. And we have negative 1 to the nth power over n squared plus 1. And this time, the question on 27 is asking us to determine whether the series is absolutely convergent, conditionally convergent, or divergent. So this is the question at this point. Good. So again, to make sure an, negative 1 to n over n squared plus 1, but bn is only 1 over n squared plus 1. Okay, so number 1, is bn plus 1 less than or equal to bn? This one is 1 over n squared plus 1, and this one is 1 over n plus 1 squared plus 1. The denominator here is bigger than this, so the first condition is fulfilled. Now, number 2, let's see if the limit as n approaches infinity from 1 over n squared plus 1, is this 0? Yes, it is. So the second condition is fulfilled as well. So we will conclude that the sum from negative 1 to n over n squared plus 1 equals 1 to infinity is convergent. It is convergent by the alternating series test. So one thing I wanted to go back to okay, so for now we know that, where was I here? So for now we know that this series is convergent. We want to see if it's if the series is absolutely convergent. Okay. So the question is, and that's number 5. The question is now if this is convergent. Okay. If this is convergent, then we conclude that the original series is absolutely convergent. So we have several options here. One option is this. We know that, again, here the denominator is bigger, so that the fraction is smaller than this one. We know that this is a p-series with p equals 2, which is convergent when n equals 1 to infinity. So by comparison, if the bigger one is convergent, the smaller one is also convergent. So we will say that this is convergent by the direct comparison test. So we will conclude then, because we showed that in the previous step that the series is convergent, by the alternating series test, and now we also conclude that the series of absolute value terms is also convergent, we will definitely conclude this is absolutely convergent. Good. Okay, where are we? This was 13. Let's look at 31. And 31 is on the same page, 773. How are we with time? Okay, good, still good. Okay, so in 31 we have the series from n equals 2 to infinity, from -1 to the nth power over natural log n, of course. Good, so then we know that a sub n is -1 to the nth power over natural log n. We know that b sub n is 1 over natural log n. So step number 1 is bn plus 1 less than or equal to bn. And this is 1 over natural log n, and this is 1 over natural log n plus 1. We know that this is bigger than this because natural log is an increasing function. So the first condition is fulfilled. Let's check the second condition. The limit of 1 over natural log n as n approaches infinity, this is 0. So this is convergent by the alternating series test. Okay. So now we are trying to verify whether, or test whether, so this is page 6. So we determined that the series is convergent, but we don't know if it's absolutely convergent. So that's the question next. So we are looking at natural log n. Please remember this is a little trick or idea that we should remember. Like we had in the previous lesson, we had the absolute value, which was greater than 2 to n minus 1. And from here, we concluded that 1 over n, the factorial, n factorial is greater than n, the 2 to n minus 1, which means that 1 over n factorial is less than 1 over 2 to n minus 1. We used this in the previous lesson. So please remember that natural log n is less than n, of course, for n greater than, in our case, greater than or equal to 2. So by the same token, 1 over natural log n is greater than 1 over n. But remember, this is harmonic. This is the harmonic series, which is divergent. So this is the sum from n equals 2 to infinity 1 over n. So if the smaller, if you remember from the comparison test, if the smaller is divergent, the bigger is divergent as well. Okay, so we will conclude that the sum of 1 over natural log n, n equals 2 to infinity, is divergent by the direct comparison test. Therefore, the original series, this one, is only conditionally convergent, not absolutely convergent. So we had -1 to the nth power, natural log n, n equals 2 to infinity, is conditionally convergent, not absolutely convergent. Good, and that was 27 and 31. And finally, we want to look at last one at 37. And that is on page 773. In 37, we are asked, show that the series is convergent first. And then how many terms of the series do we need to add in order to find the sum to the indicated accuracy? So we want the error to be less than 0.00005. Okay, so first let's talk about the convergence of this series. So again, a sub n, -1 to n plus 1 over n to the sixth, but b sub n is 1 over n to the sixth. Okay, perfect. Okay, so first of all, is bn plus first less than or equal to bn? In other words, is the decreasing situation? And the answer is yes. Higher denominator, smaller fraction. And number 2, is the limit from bn as n approaches infinity 0? Yes, of course it is. So this is clear that the series -1 n plus 1 over n to the sixth is convergent by the alternating series test. Now, the second part is asking us to determine, so this was part A, and in part B, they were asking us to find the number of terms such that the error is less than 0.00005. Okay, so remember in the situation of an alternating series test, where is my page 2? I'll find it today, hopefully. Here's my page 2. Maybe, potentially, yes it is. So all we have to look at is bn plus first. Okay, so which is s minus s sub n less than or equal to bn plus first. Okay, so let's take a look at b5, and let's look at b6, and let's see what happens. So this is 1 over 5 to the sixth. This is 1 over 6 to the sixth. So if we calculate these, assuming I find my calculator, I have 1 divided by 5 to the sixth power, and 1 divided by 6 to the sixth power. And let's see what we get. This is 0.1234464, and this is 0.0000214. And in this situation, we see that the 0.00005 error is right between here. So all we need to do is choose n equals 5. That is good enough for, simply because going to B6, it will be way smaller than that. So this is smaller than 0.00005 already. So we will be using 5 terms. Thank you.